This is level 2 of the CFA program, the topic on quantitative methods, and the module on evaluating regression model fit and interpreting model results. I'm always delighted when I can link my academic experience with the professional world, at least the professional world as it relates to passing CFA exam questions. I'm going to refer you to just one sentence in this module, and the sentence reads something like, there can be really good models that have low R-squareds and really bad models that have high R-squareds. Recall back in level 1 that we had just a minuscule discussion on R-squared, and it really explains the model fitness. High R-squareds are probably better than low R-squareds. But my professors taught us that when your dependent variable is something like stock returns for an individual company, and you have just one independent variable, you're probably going to have a super low R-squared. And our professor said, just forget about R-squared when you have that kind of a model. However, here in level 2, we're in the middle of a conversation on multiple regression analysis, so R-squared becomes super important. Let me just refer you to our efficient markets hypothesis conversation. Remember, we did the Fama and French model, and because those two researchers used portfolio returns as the dependent variable, they got an R-squared of about 90%. So let's go ahead and focus on R-squared, because this is what that first LOS asks us to do, measures of goodness of fit. Then we'll do some hypothesis testing. And then that last LOS, that's going to be super easy. We'll do that in the last slide or two. We did that back in level 1 as well. So let's go ahead and start with this analysis of variance table. And so I want you just to think about a regression equation, which we've done in the previous module, where we have a dependent variable like, let's say inflation, and we have a handful of independent variables. And those independent variables could be almost anything. Maybe it's a variable for Fed attitude or Fed predictions. It could be energy prices. So just think about this model. It has a bunch of variables on the right-hand side of the equal sign. And so we can use some kind of software. I have my students use Excel all the time to perform a regression analysis, but I'm sure you guys have access to tons and tons of other software out there. So what do? You hit the go button, and what do you get? You get this analysis of variance table, which has all sorts of really cool data in it. And so the R-squared, it's also known as the coefficient of determination, which is, in general, kind of like the R, which is correlation. It's kind of like that squared, correlation coefficient squared, but it's not, when you have multiple regression, you got a bunch of them over here, so it's not exactly the same, at least mathematically. But this R-square has an interesting formula. Notice that the LOS asks us to evaluate. So R-squared is going to be the SSR, the sum of the squares regression, divided by the SST, the sum of the squares total. So we're going to have to evaluate that ratio. So think of the denominator as everything, sum of the squares total. This is like, it's almost like the variance when we did this back in quantitative methods in level 1. Think of it as kind of total variability. And then you have variability in its two parts. Total variability can be divided into the regression squares and then the error squares. And so here in the numerator, we have sum of the squares regression. And so I think it's important to look on the right-hand side of that equal sign over there on the far right. So what is that numerator? Sum of the squares regression. We're taking the difference between y bar, which is the dependent variable mean, minus the predicted values based on the model. There's the y hat, and we have it in red, and then of course we square it because sum of the squares, that's what the definition is. And then in the denominator, all we're doing is taking the same difference between the dependent variable mean, y bar, and the observed dependent variables, right? So total over just the regression model. So this is kind of a measure of a goodness of fit. Let me give you just a silly professional sports example. Suppose we're trying to predict the number of foul shots that LeBron James takes in a game. Suppose that mean is about 7. And so think about a model in which we come up with, over the next 7 games, our model predicts that LeBron is going to shoot 14 foul shots and 26 foul shots and 47 foul shots and 82 foul shots and a minus 11 foul shots and a minus 16. Was that 7? I don't know if that was 7. But think about that. If the mean is 7 and we predicted all this stuff, our model shows that we have all these crazy outcomes. Well, that's probably going to be a totally worthless regression model, and that R-square will probably be close to 0. I never came up with a model that had an R-square of 0, but I probably had some close calls when I was a graduate student. So think about that ratio as R-square. How much of the variability in that dependent variable can be explained by the model, right? So what do we want? We would love to have perfect ability to fit the data into our model, so 100% R squared. I mean, think about this. If you took on the right hand side of the equal sign the returns to, let's say, the Vanguard 500 index fund, and on the left hand side as your dependent variable you took the S&P 500 index returns, right? So they're the same thing. Well, that R squared is probably going to be 100%. Now, of course, R-square is not perfect. Remember that we talk about the limitations of regression analysis, and these are terrific exam questions. So what don't we like about R-square? It measures a goodness of fit. I mean, there's no doubt about it. But there is no statistical test for an R-squared like there was, remember, in the previous module, and then back in level 1, we did a t-test, and we did a chi-square test, and we did an f-test, and we did a z-test. You can do all these tests. But there are no tests of significance for R-square, which means that in its calculation, it's probably not going to be able to come up with any kind of a bias in the coefficients or any of the estimates. And then look at that third bullet point. This is what I was telling you earlier about that one sentence in the module. Well-fitted models can have a low R-squared, which is exactly what my professor was telling us when we would collect data on individual stock returns, and we would try to come up with some dependent variable, one independent variable like dividend yields or changes in operating cash flow or quality of management, whatever it was. And we get these terrible low R-squares, and my professor used to say, forget about it. But then when I wrote my dissertation and I had these cross-sectional returns of about 2,000 different companies, and I collected data on things like, a classified board and a poison pill returns and all sorts of other things. But the problem then is, what we want to do is if our goal is to increase R-squared, then we can just add independent variables, let's just throw anything in there and see what sticks. And that's the problem with with what the module calls overfitting. So look at those boxes there. When there are too many independent variables, overfitted, yeah, that makes sense. If you overfit, you're probably not going to get the true relationship. I mean, if we go back to my LeBron James example, and we're trying to predict the number of foul shots that he takes in a game, what we could do is we could say something like, okay, how many minutes during the game does LeBron actually have the basketball? That's probably important, because if he has it, he's probably doing something with it, and the defense is probably going to foul him, and he'll probably he'll probably shoot more foul shots, right? But then we could add some other variables. We could say, okay, let's put a Fitbit on LeBron's arm. How many steps or how many runs? How would you say that? How many steps does he take on the court? Well, that's another variable that might be important. The more steps he takes, the more chances are that he's going to get fouled. And then how about if we could measure the sweat? LeBron, he didn't wear a headband this year, but he used to wear a headband. If we could measure the volume of sweat on his headband, maybe that's another. You see, I'm just adding variables to try to make a better prediction, but that's called overfitting, and it probably brings in other issues that we'll discuss in our next module. So then what we do is we make an adjustment. We say, okay, let's do something called an adjusted R-squared, which is an alternative measure of the goodness of fit. But what it does is it penalizes, it adjusts for degrees of freedom when you add variables. So you say something like, all right, let's add the total sweat in LeBron's headband, but we're going to penalize the model because you're adding that extra variable. So here's our equation for R squared. I'm sorry, the adjusted R squared. There's the bar over top of it. It's the SSE divided by SST, which, hold on, let me go back here. There we go, SSR and SST. So here we go. We're doing something super similar, but now we're adjusting it by degrees of freedom. So in the numerator, we have N, which is number of observations, and K is number of dependent variables minus 1. And then in the denominator, we just have N minus 1K. So I think the great exam question is to take a look at the analysis of variance output in a model that, let's say, has 3 dependent variables. I'm sorry. That's the second time I made that mistake. That has 3 independent variables, and then a model that has an extra independent variable, say it has 4. Look at the 2 R squares, and the 2 R squares probably go up. But then look at the 2 adjusted R squares, and if the adjusted R square goes down, well, then you probably are not very interested in that 4th model. Now, some rules that the module tells us is that when the coefficient T-statistic is greater than 1, either positive or negative, then R square is going to increase. If it's less than 1, either positive or negative, then R square is going to decrease. And so that's probably a good rule. Those 2 first arrow points are probably good rules to remember. So let's go back to that model that we introduced in the previous recording, where we're trying to take a look at US dollar index as functions of inflation rate and real interest rate. And you might remember this from the last module. So here's an analysis of variance output. And notice what we've done for you in the slide. There's notice in purple, SSR, and then SST. So those are purple there. And then we've done the red and the green numbers. So 432 and 632. You might remember that this analysis of variance produced this equation down at the bottom, that the dollar price index is 81 is the intercept. The inflation rate is 276 with a negative sign in front of it. The real interest rate is 902 with a positive sign in front of it. And so the question then becomes, let's go ahead and compute both the R square and the adjusted R square. And so we'll use these equations that we've had from previous. So let me just go back here. So just take the 432 divided by the 632, and you get almost 70% of an R squared. And then if you want to adjust it, then you adjust it by the ratios of those degrees of freedom. There's that equation in the, actually, if you go back here, there's that equation at the top where I was telling you how it relates to what we did earlier, but then you can rearrange this and get that equation there. So here's probably another equation for you to memorize for the exam. Although remember, the LOS doesn't exactly ask you to compute the R square from, the adjusted R square from the R square, but the reading does go through an example. So I remember going through all these when I was preparing for the exams, and I just thought, you know what, I'm better off memorizing more formulas than fewer formulas. So you guys pick. But there you go, the adjusted R square, 59, almost 60%. So you have an R square of 70 and an adjusted R square of 60%. A couple of just summary thoughts regarding what I just said and about goodness of fit. The reading does ask you to go back to level 1 as in simple regression. Yeah, multiple regression does not explain the adjusted R-square in terms of the variance. What it does is that it gives us an idea of a goodness of fit. Boy, it doesn't tell us whether our predictions are either accurate or if they're biased. What does it do? It gives us a measure of the goodness of fit. What we can do is we can use F-statistics and maybe other goodness of fit metrics to add to our understanding of the model. And so this part of the module just reminds us to think about R-square as not the end-all and the most important output of a regression analysis. It's just one of many, but it tells us some really valuable pieces of information about the model, but it doesn't give us a complete sense of how well our model works. So in order to do that, we need to perform some other tests. And so the module says, let's go ahead and do some joint hypothesis testing. So what we can do is we can just form some null hypothesis in which we say, you know what, we think a slope coefficient is equal to some number like 0. Or we think some of the slope coefficients are equal to some other number like 1. So we could say maybe slope coefficient 1 and slope coefficient 3. Maybe we think they're 1. Maybe we're trying to test if their betas, if their slope coefficient are different than the beta of the market portfolio. And then, of course, we put together an alternative hypothesis that goes just against the null hypothesis. Now, remember, in level 1, we did a lot of things like, we think the null hypothesis, we think the slope coefficient is greater than or equal to a number, or less than or equal to a number, or not equal. Here we haven't really done, and this module doesn't address this at all, and so the null hypothesis here in the examples in the reading are pretty much just that they're not equal to 0 or not equal to some other number. So there's our test coefficient for the individual slopes. So all we're doing is saying, here's our estimated regression coefficient. Let's go ahead and subtract the hypothesized value. And so in lots and lots of multiple regressions, and like, for example, in my dissertation, my hypothesized value for all of these independent variables was 0. So you're just subtracting 0 from your estimated regression coefficient, and then you just divide by some measure of standard deviation. In regression analysis, we call it the standard error of the estimated coefficient. And there in the bottom, we have some comments there on degrees of freedom, which I talked about just a little bit ago. And so let's go ahead and look at this, this top box. There's our beta, or slope coefficient sub j. And remember, j could be 1 or 2 or 10 or 50, probably not 50, is equal to v, which v is just some hypothesized value. In most cases, it's going to be 0. But if you're testing whether if you're using stock returns and you're using market portfolio returns, you might want to test that the beta is equal to 1 or not equal to 1. What we can do then is we can ask the question is, hey, let's suppose that we want to know if all of the independent variables are equal to 0 or some number, probably equal to 0. We're going to put together an F-statistic. And so F is equal to lots of stuff that we've talked about before. There's some of the squares for the regression, some of the squares for the error. Notice they're adjusted for degrees of freedom. And then look on the right-hand side of the equal sign. Those are the MSR and MSE. Those are just means. So, what do you do when you calculate a mean? You divide by n, right? Well, in this case, we're going to divide by k in the numerator and divide by n, and we're going to penalize it for some of those numbers of independent variables. And so you might get this on an output, an analysis of variance output. And so just take the MSR divided by the MSE. Now, the Institute could give you the SSR and the SSE, in which case you'd have to go ahead and divide by K and the other degrees of freedom so that you can get to the right-hand side. Yeah, so there's a picture of the F distribution. and we're going to put that critical region all the way out into the right-hand tail. That's just the way you do it. You throw everything out to the right. This is not a normal distribution. Now, what the reading does in this next section is ask ourselves the question, okay, let's go ahead and decide whether or not two models are equally of good fit, or if one model is superior to the other. So we can do an adjusted R-squared, and then the reading goes through about 2 pages on this Kika's information criterion and Schwartz's Bayesian information criterion. And here are these 2 equations. And I want you just to look at them quickly. So if you look at them quickly, you're saying to yourself, oh, wait a minute, they're the exact same equation. And of course they are, but look over to the right-hand side of the big brackets. This is where the 2 methods differ. So notice what we're doing in the AIC. We're adding 2 times k plus 1. And down here in the BIC, we're adding the natural log of n, which is probably going to be greater than 2 times the k plus 1. And so think of what's on the right-hand side of that bracket as a penalty, right? What are we trying to do? We know about R-square. We know about adjusted R-square. Well, what we're doing now is we're going to take this to an extra step. We're going to say, all right, here is a metric for us to decide whether or not adding extra variables is valuable. And it's almost like a marginal cost, marginal benefit analysis. So to the right of the plus sign, this is just the penalty. All right, so that's important to remember. That's just a penalty. I really can't imagine that you would have to compute the AIC and the BIC. The reading actually makes a comment that lots of software, in fact, almost all software does it. I know Excel doesn't do it, but most of the software out there does it. And so I'm going to give you our assessment of what's probably going to show up on the exam. So what we want is we want these numbers to be relatively low. So I want you to think about a model here. What did I say earlier? A model with 3 independent variables and a model with 4 independent variables. And the second model has an extra variable in it. So what do we want to do? When we use this AIC and the BIC, we want these numbers to be lower. In fact, the reading gives you an example where it goes through independent variable 1, 2, 3, 4, 5. R square is going up each time, and the adjusted R square goes up and up and up, and then it goes back down. And then the AIC goes up, and then it goes down. And then the BIC goes up and up and up and up, and then it goes down. And so all we're trying to do is say, look, we want to find out which of these 2 models is better for us. So pick the lower AIC, pick the lower BIC, but here's where you're going to find the most likely exam question. You use the AI criteria if you're trying to come up with a model that is predictive. In other words, you want to use a model and say, okay, what is inflation going to be next month or next year? But if you're primarily focused on the goodness of fit, then you're going to use the BIC model. And I say this not from my own opinion, and you guys know I say this to you regularly. When you're done watching this video, I want you to go to the end of the module and look at the exam questions that the Institute thinks are important. And what you'll find, there's one question on adjusted R-square, there is one question on AIC, there's one question on BIC, and there's one question on F, and then there's one question on what we're going to do at the end of this slide deck. So this is important, and the answers are predictive models and goodness of fit. And so this, you know what, get out your phone. This might be a good time to take a picture of the slide here. All right, we did that. So let's do forecasting. Here's our last one. So there's a good old model in the middle of the slide deck, or in the slide. What are we doing? X1, X2, we got a whole bunch of them. So let's go ahead and go back to our model at the bottom of the page. There's our US dollar index, inflation and interest rates. And so let's go ahead and look at the analysis of variance. So we've seen this before, last module, and then previous in this slide deck. So look at the very bottom here. Go ahead and forecast the US dollar index if inflation is 3.5 and the real interest rate is 4%. Once again, let me just remind you, look all the way over on the bottom right column. The p-value for the intercept is, boy, a bunch of zeros in there. That just means that the intercept doesn't go through the origin. Inflation rate 27, so that's not significant. But real interest rates, there's 0.145. That's less than 5%. So if we're doing 5% confidence here, inflation rate, not significant. Real interest rate are significant. So let's go ahead and predict. So our US dollar index is going to be, well, there it is. You can do the math, 107.42. Notice the LOS. The LOS says calculate and interpret. So we just did that, but I'm going to go ahead and emphasize the calculate notion of the LOS because at the end of this module, I believe it's the 5th question in that vignette, it asks you to do just that. So I'm guessing some of you thought I skipped these little blocks up at the top. So let's go back and reword these. So if we have a bunch of independent variables, when you predict, you have to include all of them, even if they are not statistically significant. So that's why here we included the 276 and the 0.035. Now, you know that the Institute, if this is a multiple choice exam question, that they're going to have the answer both with and without the, whoops, I went the wrong direction, with and without the significant variables. Yeah, so remember that, of course, we want to have a high correlation between the independent variables and the dependent variables. That just makes fundamental economic sense. But we don't want correlations between, we don't want high correlations between and among the independent variables. We're going to call that multicollinearity. And don't forget to include the intercept term, of course. All right, so there you go at the bottom of the page. And that takes us through these LOSs. And so, boy, I feel like we've done a really good job of identifying the really likely exam questions that come out of this module. This is another reason why I'm super happy and delighted that the Institute has gone to kind of shorter readings, shorter modules, and just a handful of LOSs, which gives all of the candidates, a better chance to focus, right? We want to do that laser focus. So, hey, thanks for watching and good luck studying.